Are we already on the minute? Can we start? Okay, great. So I think the timer didn't start yet. Hello, everyone. Great that you are all here. Let me introduce you to the presentation for this session together with Marie-Claude. So the session itself is on new hybrid process through additive manufacturing for increasing performance in structural composite parts. So we have two aspects. We have a processing aspect or a technology aspect, and we have an application where we showcase the technology. And this is what we want to present to you in the next 20-25 minutes. So we put it on 20 minutes, so we have some time left for questions. So I'm here with Marie-Claude. She is actually substituting for Yves, who was supposed to be here and present. But yeah, we'll manage to do it. I mean, I know it was last minute, but thank you so much for substituting in. And maybe just before I hand it over to Marie-Claude for the first section, quickly on 90 Labs. So I'm from the 90 Labs side. My name is Martin EICHENHOFER. I'm the CEO of 90 Labs. We are a company in Switzerland, in Zurich. We are about 50 people, a startup from the ETH, from the Technical University there, and we are pushing the limits of additive manufacturing in combination with composites, with continuous fiber composites, and I will elaborate it a little bit more, but not take it away at this stage. So I want to hand it over to Marie-Claude for your introduction.
My name is Marie-Claude Bélanger. I'm a project manager at CDCQ, so Composite Development Center in Quebec. Don't we see the presentation?
Huh?
We don't see the presentation?
The presentation is there.
Good.
Yeah, all good.
CDCQ is a consulting firm, R&D, product and development process, and we're part of a composite training school. We're near Montreal in Quebec, Canada. And Mawashi is a Canadian company that contacted us to help them to reduce the weight of their exoskeleton while keeping their high performance aspects. So presently, the exoskeleton is titanium printed. So it needs to be lightened, of course, and the user needs to carry heavy load on their backpack. So the exoskeleton needs to be strong. And the concept of Mawashi is the agility of the exoskeleton. The user with the concept, the user has a great liberty of movement to be able to go over many obstacles. And this is why the parts are pretty complex. When we need lightweight and high performance, we need optimization and FEA calculation. And the software suites of 90 Labs enables these calculations. Since there are many small parts on the exoskeleton because of the agility of the concept, we needed a process that was able to make net-shape parts. And of course, we were looking at high-performance materials. We have selected the Hopperwindlet that is here because we wanted to learn the 90 Lab technology and demonstrate it on a real part. And what is nice with this part is that it has a double curvature on it, and it's a good showcase and a real challenge for the 5 students that were involved in the project.
All right, then I will take it from here. So we have seen now, or Marie-Claude was talking about the challenges and the requirement of this very structural application, and it needs to be very high performance too. I think I'm missing the presentation. I'm not sure if you can see the presentation now. Yeah, here we go. So it makes a lot of sense to use or leverage fiber composites or carbon fiber reinforced composites in particular for this application. And I just want to quickly use this slide to make an entry on the next one to basically recapitulate on what fiber composites are known for. I'm usually lightweight, strong like metal, but I just want to emphasize there are some other merits of this material that not everyone is talking about too much. So radiolucency is actually something you don't hear much, but it's very relevant for medical applications. In particular. So then there's other things like corrosion resistance, okay, because it's polymer-based structures or materials, but then low thermal coefficient of thermal expansion, which is very relevant for some applications, for spaces like a known application domain for that, recyclability, there are other things. I just want to make a point that it's not just all about lightweighting and structural integrity, it's also about functional integration, it's about other merits of this material. And if we now make the transition to, as you're probably all aware of and known, that the material is not so easy to process. You know, it's an anisotropic material. It's kind of a process that has seen not too much automation. A lot of things are still based on gut feeling in a lot of cases and experience, basically. So we need kind of, in total, we can summarize that it's kind of limiting the widespread adoption for a lot of applications. And in particular, very intricate, small, complex applications. Maybe the part you have seen before is a good example for that. Like how do we make a very structural part out of fiber composites there? So how we come about this, we want to change the way we manufacture those kind of very complex, intricate parts is leveraging actually three aspects. So we are leveraging the continuous fiber, highly structural materials, high fiber volume content materials. We are bringing in automation using or leveraging 3D printing. So we have automation, but also we have basically the means to execute, have a direct integration with software and have the direct execution of a very complex design part in the software to place very directional fibers. So this gives you the potential for part optimization, which we will talk about in a second. And what we actually do at 90 Labs is we don't stop at the 3D printing level. So we introduce also, or we leverage another aspect of technology, which is compression molding. So we introduce another consolidation step. So what comes out of the printer is basically a preforming technology. And what it gives you is high reproducibility, good surface finish, good low porosity, so the void content into a part, into laminar bonding, and other aspects which are very, like 3D printing is known for not being good at. So we leverage the printer to give the automation and the optimization potential, but then we bring in another consolidation technology, a known consolidation technology, compression molding, with a proven track record to check all the final boxes for quality. And another aspect, and this other aspect I will explain you on this slide, because the approach which I just talked about, the three pillars, they translate into the Additive Fusion Technology, AFT, what we call it, and this is what you see here. And it has, I hope you can see it well, it has four main aspects, and there's a fifth aspect, which is the material, which is not described on this slide, but I will touch base in a second. So I walk you through. I will start on the left. So it starts all in our FiberFi Design Suite software. FiberFi is our software platform. So in this design suite, you're basically having tools to manipulate fiber strands to very efficiently make a very complex fiber architecture and fiber stacking, fiber layer stacking. And it interfaces directly with commercial FEA tools like ANSYS, Abacus, Nastran, and all those known solvers. So it's very much about validating the part. So I emphasize this because a lot of people always talk about optimization, structural optimization of parts, but it's not just optimization, it's also validation, digital validation of the part, before you then go into the physical world, which is then, in our case, the two-stage process. So it's the printing process where you print a preform. So that's what I meant to say by preform, because there's a second consolidation step. So it's not the final part, but it has integrity. So to print the part, it's structural, you can load it, but it's not in the final state. So it's the preform that goes into the second processing step, which is this compression module you see here, which we call fusion module. Why do we call it fusion module? Because it fuses or welds the part together, or the parts. And in this particular example, which you see here illustrated on the slide, is actually a part that comes together from multiple sub-pieces. And we actually have this at the booth as well, and you can touch it and also understand better why we do, basically why we split it into sub-pieces, print them, snap them together like a 3D puzzle or an assemblage structured, and then we co-consolidate it, mold it together with a compression molding. And you can also integrate inserts and things like that. So what I'm also here want to emphasize, it's not just about ticking the final boxes for quality, surface finish, reproducibility, all those kind of things, tolerances. It's also giving you a new design latitude on how to design parts, like spatial orientation of fibers and basically integration of things. And I will touch base on this later on, but it's not just about the quality, to improve the quality after printing, it's very much also giving a new design latitude. Then we have our workflow software, which is called Fiber from the software platform, Production, which is a cloud-based platform. It's connected to the design software, but also to all the modules, all the hardware. We are basically for every single, it's a lot about traceability too. It's like an MES, manufacturing execution system. It's tracing basically all the data accompanied with a file, from the design file to basically all the log files and the processing conditions, which are directly attached to each build or mold. So let's go one further. This just quickly introducing the materials. I mentioned continuous fiber materials. So what I meant by that is really like high fiber volume content, PKK, PEEK, nylon-based materials, very structural. And we always like show this little bit provocative slide. I mean, there are not too many like metal people maybe in this room, so it's good to show this slide. Sometimes you get a little bit like, oh yeah, okay, this is provocative, because the material itself, if you compare it in tensile loading 1-to-1 to metal, it really outperforms metals. But you have to leverage the fiber strength fully. And that's what we are doing with our technology, with the software and the combination of software and automated placement of fiber strands using 3D printing. So, and if you do it right, you can really, you can really make this happen, that this is not like a tensile test specimen comparison, that it's actually also that you leverage the strength of the fibers in the part itself, which we will actually showcase now. So this is this additive fusion technology, which we built at 90 Labs, and which you can also see later if you like at our booth. But here for this presentation, we had this very nice collaboration with CDCQ and Mawashi on the application side to showcase the technology. And what we do, and what Marie-Claude will now talk about in detail, is we use the design suite software, the Fiberify design suite software, to optimize the fiber design. Also leverage simulation to make an optimal fiber design or optimal part design. Then we printed it. We have, in this case, multiple printed preforms. And that's because the part is actually bent, right? It's a double curved structure. And Marie-Claude will talk more about this, why we do multiple sub-pieces that come together in the fusion module and the compression module to shape and fuse together, weld together the final shape, which you see in a second. So having said that, I want to give it over to you to introduce like how we did it. Yep.
All right. So Mawashi designed the titanium parts of the exoskeleton. So they gave us the load cases of the metallic part. So we had something to work with, and we use that design. We use the data to design the fiber path to get similar performance to the metallic part. And we started with full layers close to the body. Whoops. Okay. So near the shoulder. And after that, we designed continuous fiber paths from the anchor point to the tips to add performance where it was needed only. And the prints were split in 9 different layers. It was like 90 labs, 9 layers. Because if they were thicker, it would have been difficult to place the prints in the mold because of the double curvature. And to confirm the performance compared to the original titanium part, we made digital image correlation tests at CDCQ So the DIC it measures the deflection of the part under load. And as we can see from the two pictures there, the deformation is similar to the original part. So it was a great thing.
Thank you.
Okay.
And maybe, I mean, it's your pleasure to, I think, also show it, like, because this is one of the final parts we had. I think there are a few, we brought a few parts, like half a dozen parts here to the show. So if you're eager to also take a look, feel free to kind of stop by at the booth. Like we had Q88 over there in Hall 5, or we also have a few parts here, and Marie-Claude also can explain and show you the parts. So, I mean, it's a very, for us from 90 Lab side, this was a very, very interesting project and very great collaboration. And hopefully we also continue to really optimize a structural part which has a titanium baseline. And what you see here on this slide is that we could not just like match the titanium part, we could really outperform it by weight a lot. So closing in on 60% weight reduction against the titanium printed part, which is also an optimized titanium printed part and not just a metal milled part. So that was actually very nice to see, and in particular also what Marie-Claude showed before, that this, it's not just, I mean, about strength, it's also about stiffness in some applications, and in particular this one. So we could be very close to the titanium baseline in terms of stiffness, which is, as you might know, very hard with doing with fiber composites. So that was a great result. And then also some people ask about, okay, what are the costs, you know, leveraging 3D printing, you know, it might inherently be a little slow process. It's true, it might be not like a very like bulk metal, or like maybe not bulk metal, it's a wrong comparison here, but like a BMC, you know, where you just pour in like short fiber chips and then it's a very, very quick process of producing parts. But if you leverage the fibers in the right manner and automation gets quicker and quicker and quicker on the printing side, it can be very cost efficient. So in this particular case, and that's also an inherent problem of printing, 3D printing of metals, that they are costly. So there's a significant weight cost reduction compared to the titanium printed baseline part. But to also stay with me, because it's also very cost competitive against metal milled parts. So it's not just about running against a printed baseline. We also have a lot of applications where we run the cost calculations against the metal milled or casted even baseline part. So maybe also here to give a little bit like the total impact or outlook on, you know, this is a fairly small part, but if you just imagine how an exoskeleton, and this is a particular like a human-inspired exoskeleton, has a lot of sub-pieces, and they're a little bit smaller, a little bit bigger than this one, around the thighs, they're significantly bigger than this one, all very complex, intricate parts, shaped, curved, they all need to be very optimized and lightweight. So the impact we can have leveraging, and they're all applicable using the AFT technology, so the impact we can here do on this kind of spectrum of applications. So exoskeletons, a broad spectrum, you know, they're for medical, they're for kind of supporter workers in the automotive industry. So there's a lot of different applications for exoskeletons. The impact we can have is very significant. Just imagine we can create with this kind of approach an exoskeleton that's like closing in on 3 kilograms in total mass for a passive exoskeleton. That would be really a paradigm shift in that space. And it's a very good example of how to leverage the AFT technology. And maybe here also to recapitulate a little bit like on our lessons learned. I think it was a process. In the beginning, we were like looking into, okay, what are the requirements? Like when Marie-Claude was like talking about the challenges and the requirements, near net shape, there's no post-processing and those kind of things. Then we basically came up with the approach, we manufactured the part, we tested it, and here it's a little bit the summary of what we learned. So near net shape curved parts are possible, so no post-processing, no milling operation. There's no inserts integrated, but if you need metal inserts, you could technically also directly integrate them into the part. We demonstrated this digital workflow of a digital twin, so we leveraged simulation not just to choose the fiber orientations, we also validated the simulation results using DIC and mechanical testing, where we had very good correlation. And we really saw that we could also get very close to the stiffness requirements for a titanium or a metal part in general. The weight reduction potential I already showed to you, so we landed at 56% for this particular part. But here maybe also one thing to add, it's still in a metal envelope. So this is actually the exact same global geometry or the physical envelope as the metal titanium part. And as most of you know, that this is not ideal for composites, but it's sometimes usually we go in, and this is like what we do in the beginning to have a benchmark one-to-one comparison. But just imagine if we can open up that design space and optimize this part further for being a composite design and not a metal design physical envelope, like global geometry, we can even reduce the weight reduction, or we can save even more weight and have a better weight reduction beyond 60%. And the last point, I think that's also important to mention, this AFT, Additive Fusion Technology, which we developed, that it's actually, also we did kind of calculations, we talked about like how is the processing working and is it scalable, and it is. I mean, it's very much a good technology approach for high volume applications, like we are talking about a few thousand, beyond 10,000 parts a year of each configuration. So it's a very quick process, and if you want to learn more about it, talk to us. We also have a small booth just like across the hall in Hall 5Q88. It's close to the 3D printing village. We have this part, we have other parts to show, and yeah, happy to elaborate more. And feel free to have questions, because I think we have some time left. It says like 3 minutes and 36 seconds.
Thank you.
Go ahead.
Good afternoon. Dave Ivankovich here from Northrop Grumman. I had two questions, and they're both on the printing portion of your process. Question one is the raw material, the filament. Is that just a continuous fiber combined with some kind of polymer, PEC, or nylon PEEK? And question two is this a 2.5D printing process where you literally layer upon layer upon layer equals Z offsets, or is it a true 3D where you're really following you know, in all axes, the contour of the desired end configuration? So those are the two questions. Thank you.
Right. I will take this one. So actually, I start from the second question. So it's actually what we leverage is a Cartesian system. So we print the parts flat. So there's no kind of like out-of-plane orientation at that stage. To be also giving you some context, we actually come from robotic 3D printing, so come from kind of AFP kind of style printing. That's what we did in the original days. And we understood that there was a learning process really much, very much with the customers and the applications, that actually how we create now this out-of-plane orientation is through the molding. And it could be by reshaping, but there are also more complex processes you can actually trigger, very deliberately trigger, to have very complex out-of-plane fiber orientation. So to answer your question, we print in the software, we design them flat, but we can also in the software make them then curved, because for simulation you want to have then the fibers curved. That's what we can do in the software. And for the manufacturing, it's printing flat and then reshaping. And the first part of your question regarding materials, actually a very hard question to answer for startups. So we're startups, so at some point we had to lock in the materials. What we did is we say we want to not reinvent the materials, so we go from the existing supply chain on thermoplastic continuous fiber tapes, and we make those tapes accessible to the machine. So you basically have access to all the off-the-shelf and basically only standard materials which we have, which are the continuous fiber thermoplastic composite tapes at very high fiber volume contents. Yeah. Thank you. All right.
We're good?
I think there's a question in the middle. Yeah.
Thank you, Mark. Yes, thank you for the talk. Always a pleasure to listen to you. My question a little bit repeats the previous question, because you called the materials in your slide 90 lab materials. So is it possible to take the material from the provider and to feed, or you do some additional treatment such that you call it a 90 lab material?
Yeah. It's a very good question. So in general, like we understood, it needs to be, it's an open platform approach. So we're not saying we're locking in you on our materials, but we have standard portfolio materials, which we know the processing conditions and which we offer, but it's not like limited to that. And special treatments, actually, we very much focus on leveraging the existing supply chain for fiber composites. So everything you can imagine in thermoplastic composite, tape processing, this is what we kind of deal with and work together with partners. Yeah, so yeah, that's the answer. Cool. I think the timer is out. I'm not sure, like, how strict people are. Like, if you have more questions, feel free to stop by. We will be both, like, also walking over to the booth, and we have a few other parts to show as well. And yeah, happy to talk to you and engage further.
Merci.
Thanks so much.